Okay, yeah, so good afternoon here. So we treated matter yesterday. So let's no in the previous video that was matter then. Yeah, we are going to be discussing particulate nature of matter, the chemical formula and equation, that's chemical formula and chemical equation. Then lastly, laws of chemical works, reaction. So throughout these three things, I believe we should have a very solid understanding on what matter actually is, just like what I have started with. So we move. So from what we have here, the definition. Okay, we discussed this in the previous video. Okay, anything that has mass and occupies space in the sense that it does has volume. So every object or substance is made up of matter. You know that already. Many of the properties of behavior of substances can best be explained by assuming that all substances are composed of small particles called molecules. This is where we are going today. So the matter we were discussing in the previous class, we are now saying that those matter they actually what contain what small particles called what called molecules. I Let me just chip this in. When they say they have mass, give me a unit of mass. We can say something like okay grams. Then let's say the mass of the body is 10 grams. That means if we divide that body into grams, we are going to have 10 different what grams. Do you get my point? Those are what small particles or molecules. Do you get my point? That's just that. So the assumption that matter is made up of tiny particles, which are molecules in this case, which are in constant motion is known as what the molecular theory of matter. That's just the idea. The molecular theory of matter is just telling us that matter constitutes of molecules that are in what constant motion. So let's move on. So evidence of the particle nature of matter. So what are the evidence? How do we know that? Like, why do we just come to the conclusion that matter actually kind of contains particles as the basic part of them? So many substances in solid form can easily be crushed to powder easily, e.g. rather, we have piece of chalk. You know, when you can crush your piece of chalk into what? Into powder, a lump of clay. Those powders are just representing the particles, individual particles of in that what in that matter. Okay, a dry stick of wood is easily broken into smaller bits. You understand that? Solubility. When you drop sugar that has, I mean, matter is occupying. So when you drop it into water, what happens to it? It kind of deteriorates or kind of dissolves or disappear. She gets so. And when you scrape the surface of a piece of chalk, you see particles flying. Or what we also call the Tyndall effect. When a beam of light is actually entering a dusty room, you start seeing some particles flying around. Those are the evidence that okay, there are particles in what in matter. Very important. Okay, so from there we have experimental evidence of the particle nature of matter. This is just like an experiment. You may not really pay so much attention here, but let's just look at this. Experimental evidence of the atomic or molecular nature of matter is the Brownian motion. Not this. So like it is an evidence like okay, the Brownian motion. It's actually a motion that this guy Robert Brownian, she gets as far Nigerian, she get. So the motion assumed by the particles of matter, she get, which is kind of random. It's called it was discovered by the guy called Robert Brown. Then they now named it after the guy, which is now what Brownian motion. So he discovered the phenomenon in 1827. We are not concerned with that. While he was observing tiny pollen grains suspended in water under his microscope, Brown noticed that the tiny pollen grains moved about in zigzag paths. That's Brownian motion. Is a random motion that you cannot as you cannot really see this is the direction of it. It's zigzag. It is kind of hazardous. You get my point. So, but even though the water appeared to be perfectly still, pollen grains were being knocked around here and there by the molecules of water that were vigorously moving around. That's just the idea behind that. Let's move on. So the molecular motion in gas, which is the Brownian motion, note that is a random motion. And what's a random motion? Is a motion that you cannot really at a particular time say this is the direction of that motion. It is just random. It is random. And when you say something is random, I can just say, okay, five. Five is just so random. I can just thought of five. I can just say, okay, 728. It's just so random. So the direction they assume can just be anything out of like a million. Okay. So binary motion can be demonstrated by smoke cell experiment. The apparatus, okay, the figure is not shown here. Maybe the next this thing. Okay. So collect some smoke from a smoldering piece of cloth or wood by means of a syringe and introduce it into the cell. Replace the cover quickly and adjust the focus of the microscope until the fine particles come into view clearly. You will observe the smoke particles as black dots which move about irregularly like a drunken man staggering about. You understand that like you can just move to any direction. It is just telling us that the particles in what in matters move what randomly, which is the Brownian motion. So that's just that about that. So the chemical formulas and equation. So chemical formulas and equation basically we are not. This is more like a jam class. This is not this is not an elementary class where I need to start telling you guys we have 118 elements. Although we are still going to talk about that in periodicity, but you know that okay, the first 20 elements, sodium, we know that symbols and all. So for chemical formula now, it's a way of presenting information about the chemical proportions of atoms that constitute a particular chemical compound or molecule. Okay, we have a compound CO2. So the chemical formula for that guy, which is CO2, is just telling me that okay, the proportion of the what of the atoms there. And how do I represent it? I use what? The symbols of the atoms, and I also use what? Numbers. So you get using chemical element symbols, numbers, and sometimes other symbols such as parentheses, dashes, brackets, commas, and plus. When you get to organic chemistry, you understand all these dashes and all commas. And then a chemical formula is not a chemical name and it contains no word. CO2 is not a name. Shey you get? It's not just like okay, it is not. Do you get my point? It's just it does not contain words that you feel you should can just. It's just like with letters and what and numbers and all those guys. So the simplest type of chemical formula are called empirical formula. This part is very very important. The simplest types of chemical formula are called what empirical formula. You are going to see what empirical formula is, which use letters and numbers indicating the numerical proportions of atoms of each type. What empirical formula is giving us is the proportion. Okay, in CO2, I have 1 ratio 2 for carbon and oxygen. But when you have something like um there's more than let's say for example glucose. I think I gave that example. We are going to see that. But what I just need you guys to note here is that empirical formula is noting what the proportions of the what of the individual atoms. While molecular formula indicates the simple numbers of each type of atom. Okay, in the real molecule, in the real compound, how many atoms of this guy do I have? That's what the molecular formula will give you. So you get so that means your empirical formula is just kind of like a kind of like lower, like when you divide through. We are going to see that. We are going to see that. Let me just be too forward. So, for example, the empirical formula for glucose is CH2O, which means for one carbon, we need two hydrogen and then one oxygen. That's like 1 ratio 2 ratio 1. That's what the empirical formula is telling us. Do you get my point? Then the molecular formula is going to be what? 6H12O6. That compound actually has what? 6 carbon, 12 hydrogen, and what? 6 oxygen. That's just the difference between empirical and molecular formula. Empirical formula is telling me the proportion, while molecular formula is telling me the number of atoms of each guys. As simple as that. So moving to the next thing. So the chemical okay, we are still on the chemical equation now. So what happens to matter when it undergoes chemical changes? Don't forget chemical changes their what? Their chemical composition, yes. It changes their chemical that means something is being converted to another thing. That's why they say this substance have been formed. These substances have been formed. That's the idea here. So chemical equation is just an equation showing me how a compound, how a substance is being converted into another substance, or it may not be just a substance. How two or more, or maybe just say one or more, in this case, being converted to different kind of substances. So the law of conservation of mass says that atom are neither created nor destroyed during any chemical reaction. Thus, the same collection of atoms is present after a reaction as before the reaction. For example, I have 5 carbons before the reaction. After the reaction, I'm still going to have 5 carbons. It is the only thing that is happening during chemical equation is rearrangement. Not that word. It's rearrangement. So chemical reactions are related by chemical equations, of course. For example, hydrogen gas can react or bond with oxygen gas to form water. So the chemical equation for that will now be 2H2 plus O2 to give me 2H2O. Look at what happens there. I have 2H2 before, I have 4 hydrogens before the reaction. After the reaction, I still have 4 hydrogens. I have 2 oxygen before the reaction. After the reaction, I still have what? 2 oxygens. Atoms are neither created nor destroyed, but are what converted from one form to another. They are just being rearranged. That's just the idea. Okay, so consistent with the law of conservation of mass, the numbers of each type of atom are the same on both sides of the equation. That's just that. That's a fact you need to note. Then the chemical reaction changes only the distribution of atoms. not the number of atoms, the distribution, the arrangement. Let's note that. So the laws of chemical reaction. So laws of chemical reaction basically they are just four. And you have the law of conservation of mass, law of definite proportions, or the Prost law, or the law of constant composition too. Then law of multiple proportion, then lastly law of reciprocal proportions. So we're going to take them one after the other. I think I explained everything in the next slide. I don't need to do that. Yeah. So let's take law of conservation of mass. So the law of conservation of mass dates from what Anthony Lavoisier, that was the guy that actually gave us the law, Lavoisier. Lavoisier is also the guy that also talks about clearing, if I'm not mistaken. So discovered that mass is neither created nor destroyed in chemical reactions. In fact, there is a general saying that the mass in the universe is a constant. You don't destroy mass, you don't create mass. Same thing with energy, but that's for law of conservation of energy. Okay, in other words, the mass of any one element at the beginning of a reaction will equal to the mass of that element at the end of the reaction. The mass does not change, but the arrangement changes, the distribution changes. If you account for all reactants and products in a chemical reaction, the total mass will be the same at any point in time in a closed system. Lavoisier finding laid the foundation for modern chemistry and revolutionized science. Basically, that's what they use in everything, even in biology. There is reaction chemical equation for what respiration. The mass before is equal to the mass after. That's just the idea. So, for example, combustion process. When you burn a wood, you may be like, okay, the wood turns to ashes, and ashes is lighter than the wood. No, it's not just ashes that is formed. You formed when you burn wood, you need oxygen. After burning, carbon dioxide comes out, water vapor comes out, and ashes. So if you sum up the masses of all those guys together, they will be equal to the mass that they started with. Very important. Then chemical reactions. To get one molecule of water with the molecular weight of 10. Hydrogen with molecular weight of 2 is added with oxygen with molecular weight of 8, thereby conserving the mass. Very, very simple. H2O is 2 hydrogen, which is 1 grams each. Oxygen is 8 grams, making what? 10. So we add 2 hydrogen to what? To 8 oxygen. Very simple. That's 10 too. That's law of conservation of mass. It's just stating that the mass before reaction is equal to the mass after reaction. So the second law now, law of definite proportions. So the law of definite proportions sometimes it's also called the Prost law because that's the guy that did it, just like the Brownian motion. I don't know why they didn't call that one Brown's motion. So Brownian motion, this is what Prost's law. So it states that any chemical compound always contains the same element in same proportion by mass. In fact, you can emphasize this fact that okay, any chemical compound in any position on Earth, for example, in London now, when you have water, water will be H2O in London, water will be H2O in Nigeria, irrespective of where you are, irrespective of what you are, if it is water, water is still what H2O, the same what definite proportion. The proportion is definite. One earth cannot be H2O now and be H2O tomorrow. It is what is a definite proportion. That's just the basic idea behind it. So have you ever wanted to make more food? This is just like an illustration. Have you ever wanted to make more food than a recipe called for? Let's say you have a chocolate cake recipe that feeds 4 people, but you are going to a birthday party that will have 8 guests. You will need to double the rice recipe, of course, which also means you will need to double the amount of egg, sugar, flour, butter, blah 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 that you use. Okay, the amount of each ingredient will double because what we doubled what the amount of guests. That's just the idea. For example, no matter what the molecules of water you have, let's say for example, I have 1,000 moles of H2O. The ratio between the proportion of hydrogen to oxygen in that water will still be 2:1. I don't know if you get my point. That's just the idea. So and every other thing is just talking about Joseph Proust. So, okay, moving to the next. Examples of definite proportion. Okay, water. Okay, I've explained this. Okay, now the amount of water, whether it's 2 moles or 54 grams, irrespective, it's still always what 2:1. Irrespective of the amount of cake you want to make, the ratio of egg to sugar to butter must be the same thing. You cannot be using 2 cubes of sugar for maybe small cake and still be using that 2 cubes of sugar for a very large volume of cake. No, the proportion will increase. You get it's just ratio. That's the idea, yeah. So let's move on. Moving to the third one now, the law of multiple proportions. So the law of multiple proportions says that when 2 elements combine to form more than one compound, the mass of one element which combines with a fixed mass of the other element will always be a ratios of whole number. This is what this guy is saying. For example, oxygen combined with carbon, oxygen combined to form CO, and oxygen also combined with carbon to form CO2. right? Look at the ratio of oxygen in both in CO it is 1, in CO2 it is 2. It's just what? It's a simple whole number ratio. It's a simple whole number ratio. You're not having something so cumbersome like, I don't know if you get my point. That's the idea here. That's the simple and basic idea here. So what I need guys to get out of this is that they are actually what relating. Look at let's look at the law again. It states that when two elements combine to form more than one compound, the mass of one element, which combines with the fixed mass of the that element, will always be ratios of what whole numbers. Look at the condition here. The other element must be of fixed mass. It must be the same atom. In our case now, CO and CO2. C is constant. It is the O that is changing. Then the relationship between the O is what? Is a simple whole number ratio. Okay. Let us remember that the law of multiple proportion only applies to compounds composed of, I think I've emphasized this. You should not be comparing this SO2 and CO2 because S and C are not just the same thing. Compounds are made up of atoms of different elements. There are compounds made up of same elements like carbon monoxide and carbon dioxide. We have carbon and carbon in carbon monoxide and carbon dioxide, oxygen in carbon monoxide and oxygen in carbon dioxide. But the oxygen there is in what different proportion. That's what we are having multiple proportions. Do you get my point? So both compounds are made of carbon and oxygen. However, the ratio of carbon and oxygen in each compound is different. This illustrates what the law of multiple proportions. So demonstration of the law of multiple proportion. This is just what I've explained earlier. Look at this NO. This is in the case of NO and NO2. In NO, we're having like 14 ratio 16. Like the grams actually, so you get 14 ratio 16. Then in NO2, we are having like 14 ratio 32. So if you are looking at the system ratio 32 is still like the same thing. Let's look at what we have here. If you round the atomic masses, nitrogen has an atomic mass of 14, oxygen has that of 16. So far, so for nitrogen monoxide, we can say that it is made up of 14 parts by mass nitrogen and 16 parts by mass oxygen. That's for nitrogen monoxide. That's like 14 ratio 16. For nitrogen dioxide, it is what? 14 ratio 32. The ratio mean mean that for NO, for every 1 gram of nitrogen, there is what 1.143 grams of oxygen. If you divide both sides by the smallest one, look at we have 14 ratio 16, right? So divide by 14. I'm just trying to make sure that for 1 gram of nitrogen, I need what 1 point what 143 grams of what of oxygen. Why for the other guy? For every 1 gram of for NO2, for every 1 gram of nitrogen, we need what 2.286 gram of oxygen. If you check the ratio between 1.143 and 2.286, it will be a what? It will be a simple whole number. It will be like 1:2. Do you get my point? That's just the idea between multiple proportions. So then finally to the last guy. So the law of reciprocal proportion. The law of reciprocal was proposed by Jeremiah Richards in what in 1972. It says that if two different elements combine separately with the same weight of a third element, listen to this. If two elements combine separately with the same weight of a third element, the ratio of the masses in which they do so are either in the same or simple multiple of the mass ratio in which they combine. Okay, for example, now oxygen and sulfur react with copper, like kind of says oxygen with react with copper, sulfur react with copper, respectively. So sulfur and oxygen also react with each other now. It's like sulfur and oxygen react separately with the same compound, then the second phase they now react together. That's what we are trying to look at here. So in CUS now, is the mass of copper is 63.5, that of sulfur is 30. So that's 63.5 ratio 32. In CU, 63.5 ratio 16. So you can ask, okay, that's like 32 ratio 16. We have 2 ratio 1 for SO in the two compounds, right? Yes. Let's now come to SO2. We're having um in SO2, that's S ratio O is going to be what? Don't forget S is what? 32. Oxygen is 16, but 16 times 2 is what? 32. That's what? 1:1, right? So let's now look at the two ratio now. Let's look at the two ratios. So the two ratio is like we are having 2:1 for the first guy, then 1:1 for the second one. It is like simple multiple ratio. That's just the idea here. You are not having something so cumbersome or something so huge. It is just simple ratio, just reciprocal. Like they are kind of reciprocals of each other. And that's just everything about the laws of chemical equation. We have the law of conservation of mass, law of definite proportion, law of multiple proportion, and law of reciprocal proportions. So in the next class we're going to move in details into what atoms and then periodicity. So thank you.